All right, so a couple more on this sheet here. Any other questions on number 3 or first page? All good? All right, let's talk a box. A box is to have a square base with an open top, and we'll have a volume of 3 feet cubed. Find the dimensions that will minimize the amount of material used. A box with a square base and an open top. All right, so let me see if I can draw one of these guys. So I've got a box. The top's open. So let me, let's see, I'm trying to think how I'm going to draw this. So there's my top. So the base and the top is square. And so that means these dimensions are go all the way off. All right. These dimensions are on the base, so we've got there, so it's going to come back here, so forth. So the base dimensions are square, so I've got the same dimension here as I do here. Let's call those x. Okay? So the base is a square. Now we have one other, on a box you need length, width, and height. So the length and the width are the same on my box. What about the height? Well, it doesn't tell me what the height is in relation there. So we'd call that something else, call it y. It may be the same, it may not be. Probably not. But we do have three dimensions. 2 of them happen to be the same. The length and the width are the same, the height. All right. So we want to minimize the amount of material used. Well, what we're talking about minimizing here, isn't that the area, the surface area? So we'll minimize all the area of my surfaces. So let's just call that S. All right, what areas, surface areas do I have? Well, I have the bottom, so I have an x by x, x squared. Then I have the sides, which the right side here is an xy area, but notice the left side is also an xy rectangle. What about the front? Front's an xy rectangle, and the back is an xy rectangle, and there's no top, so it's open up here. So it's just the bottom and the 4 sides, and the 4 sides happen to all be x by y. So there's 4 xy's. If this one had a top, I would have 2 x squareds, but it said there is no top. So the surface area that I want to minimize is x squared plus 4xy. Well, guess what I have to do here? Again, that's in 2 variables. I need it in 1 variable, so I need to get rid of 1 variable from another equation. Well, the other equation in this case I'm dealing with is the volume. And what do you know about the volume of a box? Length times the width times the height, which in this case, the length is x, the width is x, and the height is y, isn't it, of my box? The length and the width are the same. I called them x. So that's x squared y. And I know I want that to be 3. So what do I want to do with that? What do I do with that? I want to divide that. Yeah, I want to solve this one for y. And I can plug that in for y and the other one. So I have s equals 4x times 3 divided by x squared now. I now know y is. Okay? Same deal in all of these. Really, you've got, on these, you've got two equations. One of the equations you use to substitute into the other equation. That's pretty much on these how it works. I think the last one we do doesn't quite work that way, but generally speaking, that's how these work. You got one equation you want to minimize, and the other equation you use to plug into the other equation. So anyway, all right. So let's see. What are we going to do with that? Well, we can clean up the s here. S equals x squared plus, let's see, 4 times 3, so that would be 12. And then my x is going to cancel into the x squared and leave me an x in the denominator. So I get x squared plus 12 over x. Does that sound right? Does anybody believe that? I believe that. Well, that's what I want to minimize. The minimum usually occurs at a critical number, so I need to get the derivative here. So the derivative is x squared, so the derivative would be 2x. And then again, like I said, you could use the quotient rule if you want. I like to just say, well, that's 12x to the minus 1, so that'll be minus 12x to the minus 2, won't it? There be. I just use the power rule on that. Either way you want. Which is 2x minus 12 over x squared. Is this okay? So the critical number, again, that does not exist, x is 0. That one's out. So I'm just going to set this equal to 0. See what that gets me. So how would I solve that equals 0 equation like that? How would you do it? Multiply everything by x squared, both sides, by x squared. So this side will be 0. This side will be 2x cubed minus 12, won't it? Because x squared times 2x will be 2x cubed, and then x squared times minus 12 over x squared. The x squareds cancel out, so it's just minus 12. So I have 2x cubed minus 12 equals 0. Add 12 and divide by 2. So x cubed is 6. So what is x? Real number wise, x would be cube root of 6. Okay. There's two other answers there, but they turn out those are imaginary. Just FYI there. But anyway, in case you're curious. The cube root of 6 is the one we want, obviously. All right, what was the question? Find the dimensions that will minimize the amount. All right, so the minimum is going to occur at the cube root of 6. The y, so that's the base. The length and the width is cube root of 6. The y then is, well, it's 3 over x squared. And so that would be 3 over the cube root of 6 squared. Over cube root of 6 squared, which approximately, what do you get on that? See, the cube root of 6 is, thank you, 1.82, and the y is 0.91. Again, just FYI for you here. The cube root of 6 squared. Do you know how to clean that one up? Well, I've got the cube root of 6 squared on the bottom. And so to clean it up, if I multiply by the cube root of 6 on the bottom, what does that do for me? Well, I have the cube root of 6 squared times the cube root of 6. Won't that just make the bottom, what would the bottom be then? Be the cube root of 6 cubed, which would be 6, wouldn't it? And then the top is 3 times the cube root of 6. With me? This times this is the cube root of 6 cubed. Which the cube root of 6 cubed is 6, which is, reduce that by 3, 1/2 the cube root of 6. Which is half of x, which is what the numbers seem to show me there. So anyway, just thought you'd know that. Let you know that. Okay.
So do you want to answer just a generalized number, or do you want to
Usually, they'll like it both ways, this way, and probably go ahead and round it off just to see where it is you're, if you were cutting this box out, if you told somebody, cut it the cube root of 6, they probably would not like that too much. So, yeah, it just depends on what they may ask you for decimal.
But do you want us to put in the line for x or just leave it like that?
Oh, like we did here? If you want to try it. Because that's kind of interesting to see how the two are related. But will I count it wrong if you don't? Probably not. All right. Number 5. Any other questions on number 4? Number 5. Box is to be made. Did y'all say B? No? Okay. A box is to be made from an 8 by 15 piece of cardboard. All right, so we've got a rectangular piece of cardboard here. And we're going to make this into a box by cutting out squares on the corners. And they are going to be the same size squares. And then folding up, so we get rid of these, and then we fold up the sides. So we'll have this, 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 and this. So we'll remove these corners here, and then so that sets up something you can fold to make into a box. Okay? So we'll fold it up along these marks here. So we'll wind up with a box pretty much like number 4, right? Like we had number 4. This one doesn't have a top either. That's right. No top. Yeah, that would add an extra dimension to this problem. Yeah, not the best form I've drawn here. Let's see. I think I did this wrong. So it comes across here, so we'll meet up like here, something like that. I don't know. Where am I? Here we go. There we go. Okay. So it meets up back here. So I actually see that part. Anyway. See number 4. Better drawing. Okay. All right. But the deal is here. What is the deal? Okay. All right. What do I want to do? I want to find the largest volume this box can have. So I want to maximize my volume. Volume is length times width times height. But in this case, here's what I need. It's all going to depend, isn't it, upon how big of corners I cut out there. So I don't know how big I want, so let's just call that I cut out X. So it's X, all the way around there. How does that relate to my box, though? Well, if you'll notice, this side right here, along the bottom down here, is corresponding to this right here, isn't it? On the figure, this right here. What would that be? Well, it's not the 15, it's 15 with these X's cut out of it. So it would be this right here, from here to here, which would be what? 15 minus 2x. It would be along the bottom here. All right, well, this side, the width of this thing right here, well, that's going to correspond up here to this, right? This is going to be the width right here. Which, same deal on that. The width right there, going from here to here, well, that's the 8 minus the 2x, isn't it? Because I've got two x's cut out of it. I've got an x up here and x down there. So the width is 8 minus 2x. And then what about the height? Well, the height, this little piece right here, what is it going to be? That's just x, yeah. So the length is 15 minus 2x. The width is 8 minus 2x. And the height is x. With me? That's what I want to maximize. Now this one, unlike the other one, we're good to go, more or less, because this one's only in terms of x. There's not a y, a second variable involved. So I'm good to go with finding, I want to maximize it, so I want to find the derivative, set it to 0. Well, a couple ways we could go with that. If I leave it like this, what would I have to use? A couple of times I'd have to use product rule, right? So let's go ahead and multiply this out. Let's go ahead and multiply the volume here out. So 15 times 8, isn't that 120? And then 15 times minus 2 is minus 30x. And then minus 2x times 8 is minus 16x. And minus 2x times minus 2x is plus 4x squared. And then times the x. So the volume is 120 minus 46x plus 4x squared times x. So times that by x, all in there. So it'll be 120x minus 46x squared plus 4x cubed. I'm going to distribute the x to all those. That sound okay to you? So now I want to maximize that, so that would be, I need to do the derivative. Derivative is 120 minus 92x plus 12x squared, right? And obviously that one's going to be, I want it set to 0. Any ideas on that? Well, one thing I can see at least, see, does 92, does that divide by 12? No. I can divide all this by 4. Make it a little easier on myself here. So I have 0 equals, what would that be, 30 minus 92 divided by 4, 23, x plus 3x squared, or 3x squared minus 23x plus 30. Which, how do we solve that? We can use factoring. We can use quadratic formula. If it doesn't factor, I think it factors though. If it doesn't factor, you can use a quadratic formula, but I think it factors. 3x and x, let's see, 10 and 3, will that work? No. How about 15 and 2? No. Well, maybe I jumped the gun saying it works. 5 and 6? Aha. Thank you. If I do 3x minus 5 times x minus 6, I get 3x squared minus 23x plus 30. All right, so if I set those individually to 0, what do I get? X is, this would say x is 5/3. And x minus 6 equals 0, so that would say x is 6. So maybe I have two answers here. Not really. Okay, here's why. If I set x to be 6, x to be 6 will not work. See why? Here's my dimensions. I'm wanting the dimensions, right? Well, no, I want the largest volume. But I can't let x be 6 because that would make one of my dimensions 8 minus 2x. And 8 minus 2x, if x is 6, would be negative 4. That's why x can't be 6. Because the width wouldn't work out. So x is 5/3. So that would put me then, so back here, yeah, so I want the x to get the maximum volume. X needs to be 5/3. So, well, I guess I could plug it in either place you want to. You can plug it up there or down here. So the maximum volume, if you want to do it length times width times height, go to that one, or you could plug it in here too. So the maximum volume so plug in x to be 5/3. I guess I'll go right here. Since I can see it on my screen. Okay. All right, so the maximum volume be that with x is 5/3. So it's 120x, so it'd be 120 times 5/3 minus 46 times 5/3 squared plus 4 times 5/3 cubed. And of course, if you wanted the dimensions, then you'd have to go back to the other one. All right, let's see. 120 times 5/3 minus 46 times 5/3 squared plus 4 times 5/3 cubed. What do you get? 90.74. Anybody have an exact value? Change that to a fraction. 2,400 2,450 over 27, or 90.74. Cubic inches, yes.